Hello community! Today we analyze Infini-attention, a beautiful new attention for 1 million token. Now you remember in my last video I showed you ring attention. We had here given me a ring topology of our GPUs. We had a permutation invariance of the system, and therefore in the inner loop we had 21 key value pairs that rotated here between our GPUs, and we could reduce here the overhead of the transmission of data almost to zero. Because we used here, while the machine was computing the new key value pairs, that the transmission to the next one and the input from the machine before happened exactly in this time interval. And we achieved at least 1 million token with an outlook to 16 million token. Now Google published on April 10 here a new Infini-attention. So let's have a look what it is. Now you have to know there's a long tradition. You see 2019 we already had TransformerXL, a tentative large language model beyond a fixed length context. And it further evolved. We had compressive transformer, memorizing transformer, autocompressors, and now the latest step in the evolution, which is called Infini-transformer. Now, it is rather simple. You see, in the Transformer XL, we had our input sequence divided in segments. No, not blocks. Now it is called by Google segments. You guessed it. In those segments here, we are simply calculated the key value pairs. Now, what is new now in the Infini-transformer? That we put here a memory element exactly between our segments. So when we start here in segment 1, and we have here some interesting information, beautiful, we have the key value pairs, and then the blue arrow says memory update. So we update here the memory, it is simply a matrix of key value pairs. And then we have a memory. And when we analyze now the local attention of segment 2, we can retrieve the memory, the pink arrow, from our memory storage. Therefore, we not only have here the local attention, but we also have here extraction here from the memory attention. And this goes on, and you go from segment 2 to segment 3, and your memory becomes more and more dense and more information. So H is the number of the attention head of our system, and of course we have H number of parallel compressive memory per attention layer. So this is the number of our green compressive memory elements. Now, whenever we compress infinity into a memory that has a restricted memory, and has the form of a matrix, you know, if we take infinity and we take a knife and we cut it in half, then we have on the right hand infinity, on the left hand we also have infinity. So you guessed it, when we take an infinity and we put it in a restricted non-infinity memory matrix, something has to give. Yes, somewhere we will lose information, but no problem at all. So for my green grasshoppers, you know what is the solution to this? We simply have a notebook where the system writes down the most important information of the last step. Or let's do it here in parallel for my advanced AI users. What we have here, the system carries a memory matrix with itself in the attention process of key value pairs of the last segment. That's all there is to it. So for my green grasshoppers, easy to understand Infini-attention by Google. So imagine you are trying to remember a very long story, a book with 1000 pages. Normally your brain picks out the key moments or the key facts, the key person acting in this book that you remember. But you know, you don't keep every single detail. What was the weather like on the day 212 on the story? So instead you jot down the important clues in your notebook. So when a new information comes in that it's important, you update your notes in your notebook, and we need to solve here a new task, a new case. You pull together all the relevant information from the past notes that you wrote down. For example, you took notes here from a university lecture, and then you have to solve a given homework. Easy. You just look up here the most important fact in your notebook and you found the way to solve here the algorithm, for example. So, very easy. You have a notebook where you have written down everything. The infinity-attention mechanism uses something very similar to a notebook, but we just call it a compressive memory block. So, kind of a super efficient notebook. And now, instead of writing down every word of the story, like we do here as humans, we use here, for example, the English language, the notebook now has only limited pages, and you can't write down everything. So you just keep the essential of the story of the last 1000 pages. However, the nice idea is, if you have a limited notebook, whenever now new information comes in, you're at page 900 and you get some brand new information. You need now to update the notebook. So you have to kick out something of the old data and you have to update the notebook with the new data from the page 900 to 950. So simple. The notebook now is an intelligent notebook, checks if the new information is just a repeat of what's already in the notebook or it is something brand new that it has to add to the story. So the system decides to update the nodes here in a very compact format, and my professional AI friends know it's a key-value pair structure. Beautiful. So we have two processes that we focus now. We update the memory matrix and we retrieve information from the memory matrix. Let's stick with the first one, updating the memory matrix. So when the computer reads here new text, it decides what's important based on what it has seen before. And it uses some rules like the delta rule, I'm going to show you in a minute, to avoid writing down the same thing twice or noting down useless information. Now you can imagine a machine that has to decide is the information valuable or not at a very early stage is not an easy task. However, so we make sure the notebook isn't filled with repeats or irrelevant details, so we write down here all the key value elements that have a high attention score. And if we use now some old information, the computer doesn't forget the older parts of the story of a 1 million token length. So when it needs to remember something from earlier, it just looks back in the notebooks in the key value pairs, it reads it and it can update its memory. Now, let's say we are now in the next sequence of our input. So we have to retrieve here the memory from the last segments. So when a computer, an AI system, needs to recall something from its nodes to understand new text better, it uses here a specific query. It's like searching for a topic in an index. And this helps us here quite quickly find the information that is stored in the earlier parts of our text in the notebooks. And then what we have then the new segment information, the new attention calculated, but we have the memory attention from the past. And now you bring together those two, and there's a balanced control mechanism that helps us not too much new information, not too much old information. We have to have a healthy mixture. Beautiful. So in Infini-attention for at least 1 million token context length, we need a notebook. This is here the solution that Google says that's great. Now, a little bit more with a mathematical background. Again, we look here at the update memory process and then we look at the retrieve memory process. So let's do the same again. We have something that is called an associative binding operator. And this comes here, you see here conference paper of ICLR 2021. This is here a historic development, historic insights we found. If you want to learn more about this, I would recommend exactly this paper here from ICLR 2021. What it does is simply, associative binding is here the process of creating linkages between the keys and the value that represent contextual information from the input sequence. And this associative binding involves projecting the input vector into a key space and a value space using here our learned projection matrices that we know. This key and value are then used to update the memory matrix, where key and V are the current segment keys and values, M is the memory matrix, So we go from the step before to the actual memory matrix. Sigma is here nonlinear activation function. Beautiful. So this is what we found from historical experiments. And now the second part is here, the delta rule. And the same is true. The delta rule is not just it happened, but it was discovered in years and years of working. So the purpose is to minimize the redundancy by ensuring that only new or updated information alters here our memory matrix structure of key-value pairs. So before updating, before modifying our memory matrix structure, the memory first retrieves any existing values associated with the current keys to determine if the new information is really significantly different from what already stored in the matrix. And this is here the simple equation. Now, the delta rule attempts a slightly improved memory update by first retrieving the existing value entries and subtracting them here from the new values before applying the associative binding as a new update. You have normalization factors and everything that you know. So you see, this is here, if you want, the mathematics of the updating process for a memory matrix. If you want to learn more about the delta rule, I recommend here particular this mathematical or this AI preprint here about linear transformers as secretly fast weight programmers. Now to the second part. Again, we are talking about retrieving now from the memory that we have updated. Now the memory retrieval process, of course, the function is to integrate now historical context from the 1 million context length before our current segment into the current processing, the current calculation of the attention. So the model uses here the current queries to fetch relevant historical data. Historical means only on our 1 million token length from the memory. And there's a simple equation where Q's are the queries from the current input segment and M, a memory, a matrix S minus 1, is the memory state from the previous step. And Z is a normalization term. And if we have retrieved the attention, and it is not as easy as you might think, there's a lot of operational know-how. We can have a look at the code and you will see this. Then it is time to combine, of course, our local, highly precise calculated attention of our segment with the memory-based attention. And we have here a simple equation. And if you look at this, you understand it immediately. So you have here the local attention with the dot product, and you just add here the memory attention. And of course, beta, you might say, what is this? This is a very specific learned parameter of the system that just adjusts here the trade-off between the historical data and the current segment data. So with beta, you can play around a little bit, but the idea now of the attention is you have your local attention plus your memory attention. So now the system should be able to solve any task that you give it if it has this access to this memory matrix in its original attention mechanism. And now this is now a real interesting question, because I ask myself at this point, hey, wait a second. Is this an internal rack system here that we have in the attention mechanism of the transformer itself? Because think about it. Retrieve, augment, generate. We retrieve here the data. Okay, we do not retrieve external data from a database that the LLM has access to, but we retrieve data within our interval of 1 million or more tokens. So if we have a segment that's somewhere here in the middle, and we look back here in this 1 million token string, so we have no external data, but if you want, we have historical data in our 1 million token data. So retrieve, yes, not external data, but historical data. Then we augment this. Augment simply means here more or less we combine the local and the memory-based attention mechanism. So we just do not have this segment attention with our classical dot product, but we have now also, we integrate, we augment it with the historical data, with the attention over there. And then generate. Generate is a little bit complex because generate would imply a large language model. But the mechanism of an LLM is, of course, attention. and we are operating here and we do attention calculation, at least it's called Infini-attention. So this is an interesting idea. So for a second, hey, is this an internal rack system? Because also the query to the key, we have something like a vector comparison in a particular vector space that is happening within the Infini-attention mechanism. So I was smiling and thought, hey, there could be a potential here to see something similar to a rack system, but on a much more advanced, much more performant system that's operating within the attention mechanism. Cool. Okay. So what is the main idea? The main idea is the integration of a memory model into our vanilla classical dot product attention layer that we know from our transformer network. And this gives us now access to very long sequence length because the memory module, remember the most important facts, data or whatever from this 1 million token string. So beautiful. And the author here says, hey, this new approach can naturally scale up to a million length regime of input sequences while outperforming the baselines of long context language modeling benchmark and book summarization tasks. So now talking about the summarization task. Let's have a look if we have a 500,000 token length book summarization task. How good is the performance of the system compared to other systems? And now they give us here in the original literature here a benchmark with Rouge 1, 2 and L and the overall benchmark. I would have thought that the Infini-transformer, especially with the delta rule, would perform much better than the other systems. But okay, we have to accept the results that there are. So as you can see, depending here on what you're looking for, yes, they are better, but honestly, I would have expected a more significant jump in the performance compared to our classical system. Now, if you are to one of my little green grasshoppers and you say, can you please repeat this in simple words? But of course, key value pairs in memory. We have an infinity-attention mechanism. We have here key and values that we store and we compute an attention. The attention matrix acts like a summary of the past input segments. And then we just do here, if we have an actual query from the new input, it just interacts with a memory matrix. And you know this mechanism from the vector store. This is simply the query retrieves historical data based on how closely the keys in the memory match the query vector. Beautiful. And then the integration and the complete attention mechanism, the memory matrix is dynamically updated each segment step as new input is processed, and the old information can be overwritten because we only have a limited amount of matrix here that we can use here as a temporary storage. So whatever is now the most important, there's now a balance, and it's a delicate balance between the memory size and the information relevance that we want to store. So Google has here found for particular tasks like book summarization here, interesting equilibriums. Therefore, this structure allows the Infini-attention to efficiently handle longer sequencing by summarizing and reusing information without the problem we have if we would refer only to the classical self-attention, where the complete complexity of all tokens to all other tokens gives us here a quadratic complexity. The nice thing that we have, this is a plug-and-play capability. Amazing! So Infini-attention supports here the seamless integration with existing LLMs, allowing here for an easy adaptation to long context tasks without some extensive retraining of our LLM. And this is beautiful. Now, of course, you might say, this was a rather simple approach, no? We just put in a memory matrix and then we calculate here the segment attention mechanism with an influence here of the past memory attention. Is this really the latest state of the art? And you might have said, hey, I would have expected a more complex theorem from Google. And before ending, I have to say, hey, wait a second, because we have breaking news. Yes, recording this video here I just found that we have a new archive, a new TransformerFAM. And this says we have now feedback attention memory. And they work here with the block structure from my first video, from the ring attention, from the block parallel transformer idea. And they combine this now with what we just learned about the memory structure in the attention mechanism. And they construct here a new attention mechanism they call the TransformerFAM, the feedback attention memory, a novel transformer architecture. And you might say, my goodness, who would be that genius? Who would be that brilliant to combine this idea? Who would have the power to come up with new? Okay, it is Google. Again, Google. That's the reason I love Google, because they communicate the ideas. They show you the step, how they go one step at a time. They build upon this, they build it more complex, they combine this. And now, for me here, April 14, now we have the TransformerFAM. So if you're interested, in my next video, we talk about the real latest development. Hopefully, if not, something new happens in the next 24 hours. It would be great to see you in my new video.